Hey everybody, welcome to Intro to Biochemistry. What I wanted to do with these kind of videos is to just show you some of the questions from every week's Action Center that I thought would be, useful to know, and go over some of the most important concepts that are covered in that week. And so we'll start with Action Center 1 this week. And so I've selected 3 questions from the Action Center. And I'll go over these as best as I can and try to explain like some of the concepts that are going on. And if you noticed, a lot of the questions in this Action Center are mostly focused on pKa stuff like pH buffering, all of that kind of stuff. And you may be thinking that these seem like very general chemistry like questions, but I would really encourage you to pay attention to these as much as you can. These are very important for biochemistry, especially later on in the semester. We care a lot about whether things are protonated or deprotonated at a certain pH, given that something has a certain pKa, and getting really comfortable with this style of question and this style of reasoning is going to help you like a great deal later on. So don't take this Action Center for granted. It is still very useful, and I'm going to do my best to try to show you these 3 questions that I think are pretty important. So we'll start with the first one. It's not really important, but this is what propionic acid looks like. You don't necessarily need to know that for the question, but essentially, that hydrogen here would come off, and you would have a deprotonated state that would lower the pH if that happened. But so to actually answer this question, we would need to do an ice table. And so the way that I always like to do this is I'll start out by writing my acid dissociation equation. And then we have our initial, we have our change, and we have our equilibrium. And so we're given that we've got a 0.52 molar solution of this. So that's our initial concentration is 0.52. And then it hasn't dissociated yet. So we'll put zeros in the H plus and the conjugate base. The change, we're we're going to be losing the HA. So we'll put minus X there, plus X's over here. And what we'll have is 0.52 minus X and 2 X's as our equilibrium. Now we are given the pKa of propanoic acid, as well. And so what we'll do with this is we can write our Ka expression. So Ka is the acid dissociation. And so that's going to be A minus H plus, over HA. And if we look back over here, we actually have all of those things. So we can write this as X times X, because those are our 2 values right there, over 0.52 minus X. And for this class, we're going to be making the assumption, I think pretty much every question that you do, we'll always be making the assumption that this X is small enough to where we can ignore it. So what's going to happen is this will simplify out to X squared over 0.52, which is going to equal our pKa, or I'm sorry, our Ka, which we're given the pKa as 4.88. So to find, we're given the pKa is 4.88. We need to be able to find the Ka to plug it into this equation. And the way we do that is we say that Ka is equal to 10 to the negative pKa, which in this case is 10 to the minus 4.88, which is going to be 1.3 times 10 to the negative 5th. So plug that in for Ka. And from there, we can just plug this into a calculator. We can solve this. What you'll get is that X is going to be equal to 0.0026 which is going to be equal to the H plus concentration. So the H plus concentration is 0.0026 molar, which means that the pH is going to be equal to the negative log of 0.0026, which is going to be 2.59. And that's our pH. Now, our second question is asking about, it's a very similar concept, but we're asking about a weak base instead of a weak acid. And so the way that we'll do it for a weak base, we'll still do the ice table method, but we'll be doing it with the base dissociation instead. And so the way that that works is it'll be A minus plus H2O will dissociate into OH minus plus the conjugate acid. That's just the general formula for base dissociation. And so we'll set it up exactly the same way where we have our ice table. And the thing to remember with like base dissociation is that the water doesn't matter. So we can ignore this column. So we're starting with 0.2 moles or 0.2 molar, and we'll have 0 of these initially. Our change is going to be, we're losing the initial and we'll be adding that same amount here. So our equilibrium will be 0.2 minus x, x, and x. So instead of a Ka, because this is a base dissociation, we have our Kb. And our Kb is going to be OH minus times HA over A minus. And so what that's going to simplify to is x squared over 0.2 minus x. So we have our Ka. So we've been given a Ka of 5.012 times 10 to the negative 10th. And so what we have to do here to actually do this question is find Kb. And so the formula here is that Ka times Kb is going to equal Kw. Kw is a constant, which is going to be equal to 1.0 times 10 to the negative 14th. And so to find Kb, it's going to be equal to Kw over Ka. So 1.0 times 10 to the negative 14th over 5.012 times 10 to the negative 10th. And we'll get 1.9952 times 10 to the negative 5th. That's our Kb. So plugging this back into this formula, this is our expression that we're going to be dealing with. And if we solve this, we'll get that the OH, or I'm sorry, what we'll get is that X is going to be equal to 1.997 times 10 to the negative 3rd, which is going to be equal to the concentration of our OH minus. So what we can say with this is that the negative log of 1.997 times 10 to the negative 3rd, this is going to be equal to our POH. So POH is going to be 2.7. And as you probably know, the pH is going to be 14 minus that. So that'll give us 11.3. So always pay attention to what the question is asking for, whether they're asking for POH or pH, or whether they gave you Ka or Kb. Those kind of small details can really make or break these questions. And so last one that I wanted to cover here was this one about uracil. And one of the questions I get asked a lot of the time is like, do you need to know what these things look like? Or like, do I need to know what uracil looks like? The answer is eventually, yes, you will. But to answer this question, it doesn't actually matter what it looks like. You can do this question without knowing what uracil looks like. And so Sorry. To do this question, we'll need to use the Henderson-Hasselbalch equation. I would say generally, every time you're going to see something like this where you want to find the ratio of unprotonated to protonated, the easiest way to do that is with the Henderson-Hasselbalch equation. So that formula is pH is going to be equal to pKa plus the log of the conjugate base over the acid. Those are molarities. And so the way this works is we have our pH and we have our pKa. So we can just plug those in as 9.0, 9.5 plus the log of A minus over HA. Now, the cool thing that we can do here is, so he's asking what the ratio of the unprotonated to the protonated form is. And that's exactly what we have here. This little part of the equation is that ratio. So we can actually solve this pretty easily. So we can simplify this to minus 0.5 or negative 0.5 is going to be equal to the log of A minus over HA. And if we do this equation, or if we solve this equation, we'll get that 10 to the negative 0.5 is going, or wait, sorry. Okay, so we'll have 10 to the negative 0.5, which is going to be equal to roughly 0.32. And so if we know that that is equal to 0.32, then that's what, that's the same thing as A minus over HA being equivalent to 0.32 over 1. So that's how we can say that the ratio of the unprotonated to the protonated form is 0.32 unprotonated to every 1 protonated.